Right. We're about to do a very short video on the relativity of the LHC, the Large Hadron Collider, to assist in an assessment task. This is just going to be a very general treatment of the relativity, and we're going to be using a very simplistic model of the LHC. So what we're going to do is we're going to start with having a model. We're going to pretend or just assume that the LHC is a massive circular collider, and into this collider we are going to place from another source just put it here, we're going to use another source of protons that have been already accelerated. So the protons are coming from another accelerator. In the actual LHC, these are from different other circular hadron accelerators, but we're just going to assume that it's coming in at some stage here at a velocity, and we're going to make this velocity, let's make it approximately equal to 50% of the speed of light. Okay. We're also going to use the radius here, and that radius is according to the spec sheets that you can get online, that radius is, let's have a look here. I know what the circumference is. The circumference is equal to 26,659 meters. And so therefore, using that as 2 pi r, we can then calculate the radius as 26,659 divided by 2 pi. And we'll then find that value. I'll just type it into the calculator I've got in my hand here. So that's 26,659 divided by 2 pi. That gives us a radius of 42,000. That's not right. Let me do that again. That's 26,659 divided by 2 pi. It's 4,243 meters. Okay, so we're just going to I'm just going to round this for simplicity at 4,200 meters here, and we'll just use those as the beginning conditions. So I'm just pretending, you have to do research to find out how much the actual velocity would be coming into the Large Hadron Collider. It's much more than the value that I've got there. But we're going to accelerate our our proton beam, to a staggering velocity of 0.8 nines, 1, 2, 3, 4, 5, 6, 7, 8 nines, 1 C. Okay, so I'm not even going to try that as a percentage, so it's 99.99999 and so on percent of the speed of light. Now at this stage, at this level of velocity, our gamma factor, now the gamma factor, as you know, is 1 over the square root of 1 minus v squared on c squared. Now this fraction v squared on c squared can be, because it contains the c squared on the bottom, would be just 0, this value up here, so it's this velocity as the decimal of light, that thing there, squared. So it will be 1 minus 0.999, there's 8 of those, 1, 2, 3, 4, 5, 6, 7, 8, 1, that number squared. Okay, because the c's, this c up here and this c down here will cancel when squared. Right, putting that into a calculator and just determining this factor gives us, okay, popping in the calculator, it equals 1054, I'm just rounding to the nearest whole there, that's 10,541. Therefore, the effect of things like time dilation and mass effect are 10,500 times more noticeable. So a good old little proton will have an effective mass of 10,500 times its own mass, its relativistic mass. So now let's work out how much magnetic field is needed to constrain a proton that goes around this circle path to make it go in that circular path. So when it first goes in, our velocity is a staggeringly slow 50% of the speed of light. Then it's going to go around our Hadron Collider many thousands of times as it goes around. And as it does, it builds up to a velocity which is this staggering number over here. When it first comes in, our magnetic field that is used to constrain, we'll assume that the magnetic field is just at places around this pathway. In reality, these are massive superconductive coils, and that works at right angles to bend the beam in a circular path. And we know that the strength of that, the amount of force required, is given by the centripetal force. So let's have a look at, copy these out, what we've got here. The centripetal force to keep that beam in a circular path will be given by mv squared on r, where v is the velocity and m is the mass of the proton and r is the radius, and r is going to maintain at that number there, 4,200. The magnetic force that is needed is given by qvb sine theta, and we know that the theta here, the angle, is going to be 90 degrees because we've made sure that it acts at right angles to the actual pathway. So it's directly, if these are the magnetic fields, then this is the pathway here. We've got it at 90 degrees. Okay, so we can effectively ignore the sine theta because it becomes a 1. Equating these two, we get mv squared on r would equal qvb. And finally, just simply cancelling it, we get mv on r equals qb. And we'll use that relationship to determine what we need as we go through. Right, now, we're going to work out what the magnetic field is needed at the beginning, when it's only 50% of the speed of light, and we're going to work out the magnetic field strength as it is required at the end. Okay, the magnetic field strength, this one here, will have to increase as the mass of the proton increases from its first relativistic mass, which is going to be here, and to its final relativistic mass, which is 10,541 times its original mass. Okay, so let's start with the original mass on entry. So let's get us a place to work with. We need to find the gamma factor at 50% of the speed of light. Okay, so that gamma factor, there's too many equal signs in that sentence. That gamma factor at 50% C will be 1 over the square root of 1 minus 0.5 squared. Okay, just doing a quick calculation on that. I'll just pause while I do it. So, okay, that value is 1.155. Okay, rounded to just 3 decimal places there. And that means that the mass of the proton is 1.155 times as massive as it would be if it was at rest in the laboratory. So using our relationship that we have over here, we are now going to work out the magnetic field that is required to constrain this particle at this point in a circle. So B would equal to mv on qr. Okay, and this m is the mass of the proton. Now the mass of the proton will be, normally a proton has a mass of 1.673 by 10 to the minus 27. But on entry, it's 50% of the speed of light. It's traveling at that speed, and therefore it is slightly more, has more relativistic mass. So it is actually going to be 1.155 times its original stationary mass, its proper mass, times the velocity, which is 50% of c, which is 0.5 c, all over its charge, which is 1.6 by 10 to the minus 19, times the radius, which is, we're just going to take this as a nice rounded number. Yep. Now the c value, of course, is 3 by 10 to the 8th. So we now will place that into that calculation, and I'm going to pause the video while I do it. Okay, and this comes to be 4.3 by 10 to the minus 4 Tesla. So we're into the thousandths there of a Tesla. So it's not much field strength that is required to maintain a particle of a proton in such a large radius. So it's a very, very small magnetic field. This is going to change, however, as the proton goes around more and more and gets more massive as it accelerates around the collider. Now we're going to try and work out how much magnetic field is required at the end of the process. So this is the magnetic field now that is required when it reaches a velocity of 0.123456781 c. Now we know at that point there that the gamma factor is a staggering 10,541, and so this number over here has grown from being simply 1.155 to 10,000, and this number here is also going to grow to a number which is the one which has the 8 nines in a row and then a 1. So let's calculate its value. So the formula as before is exactly the same. The mass of the proton now is not just simply itself, it's 10,541 times its original rest mass, and that's minus 27. I'm just going to have to move and get some more space here. We probably don't need the collider anymore, so I might just take it away. Times by the speed of light, which is 0.923456781 c, all over its charge and the radius that it's now travelling. Okay. Once again, I'm just going to pause the video and do the calculation at this point. Okay, the calculation gives us to 7.87 Tesla. I'm just rounding that so it's easier to 7.9 Tesla. So nearly 8 Tesla that's required. And that's the recorded value on their specification sheet of the maximum magnetic field that is used as the collider works. So, just in recap, we have our collider. And, oops, sorry, I'll just put that there. And our collider has an entry into it of a velocity of protons. So this velocity here, we just chose randomly at 0.5 c. As it goes around the collider, the acceleration, I'm using a resonance frequency, and in the Large Hadron Collider, there's many of those. It accelerates the proton at some stage to 0.999999, that's 6 of them, 991 c. At this point here, the effective requirement of the Tesla is approximately, actually what was the actual value? It was approximate 4.3. 4.3 by 10 to the minus 4 Tesla. At this point here, at the actual speed, we needed 7.9 Tesla. So the reason why we need such a large increase in the magnetic field is that there is a large increase in both two things. The relativistic mass increases as well as the velocity increases. And the formula that is needed has both of these values in it. The formula has both m and v. And that m and v there is simply the momentum of the particle. Okay? So v is directly proportional to the momentum. Oops, I'll just write it down. And as the momentum of the particle increases, that's, in other words, its mass and its velocity, we require a larger and larger magnetic field strength. Okay, so I hope this helps in any assessment task that you may be working with at this stage. Okay, thank you very much.